Dear friends, welcome to my YouTube channel. I am Dr. Musaddiq here. In today's video, we will discuss about the commutation and anti-commutations of Pauli matrices. In quantum mechanics and in quantum information, this topic is of very importance, and also in quantum field theory and in condensed matter physics. Let's suppose we have two Pauli matrices sigma x and sigma y. So when sigma x and sigma y commute with each other, then their commutation relation can be written as sigma x sigma y minus sigma y sigma x. Instead of sigma x, we will write its matrix form, and instead of sigma y, we will write its matrix form. And when we solve it, it will give us result of 2 iota sigma z. So what does it mean that sigma x and sigma y do not commute? Which means that they cannot be measured simultaneously and the same time. And in other way, by quantum mechanical means, you can say that sigma x and sigma y do not have simultaneous eigen functions. These type of commutational relations are used when we are talking about the bosonic spin systems which have spin 0 or spin 1. Similarly, when we evaluate sigma y sigma z, it will give us 2 iota x sigma z sigma x, it will give us 2 iota sigma y, which shows that whenever we are dealing with the commutation of sigma x sigma y or sigma z, then with different notations they do not commute with each other, which means they have different eigenfunctions. So in general, we can write this in that form: sigma I sigma j is equal to 2 iota sigma k epsilon ij. This epsilon symbol is known as Levi-Civita tensor, and ijk are indices which are representing x, y, and z Pauli matrices. So value of Levi-Civita tensor will be +1 if we are doing the cyclic permutations. Cyclic permutation means if we are taking the order of Pauli matrices in a particular pattern in which we are going from sigma x to sigma y to sigma z to sigma x. Such type of permutations are called cyclic permutations. Then the value of Levi-Civita tensor will be +1. Otherwise, if we are not following the cyclic permutations, we are going in the either way. For example, if I am calculating sigma z sigma y, then value of Levi-Civita tensor will be -1, and same is true for the other two combinations. From here, I can tell you very clearly that if we change the order of Pauli matrices, for example, sigma z comes at the first position and sigma y at the second position, then simply here will be -1. This is the anti-cyclic permutation. Okay, now if both the operators are same, for example, I is equal to j, then sigma I sigma j will be equal to 0, which means similar Pauli matrices can be measured simultaneously at the same time. Sigma x equal to 0, and same is true for sigma y and sigma z. So this was little introduction about the commutation of bosonic spin systems, and the Pauli matrices operations can be find out by these simple relations. I hope so you got it. Now let's move towards the fermionic spin systems. All you know that in fermionic spin systems we are dealing with the spin half systems like electrons, protons, and Pauli exclusion principle comes into play in the fermionic spin systems. For anti-commutation relations, we use curly brackets, and commutation relation is anti-commutation relation is written as sigma x sigma y plus sigma y sigma x. So this is the difference between the commutation and anti-commutations. When we are dealing with the fermionic spin systems, especially in quantum field theory or in quantum mechanics or in condensed matter physics, then we have to keep in mind this difference. So by using the same the other algebra is the same. By using the values of matrices, we come to the result that sigma x sigma y is equal to 0, which means that sigma x and sigma y can be find out simultaneously, and they anti-commute with each other. Similarly, sigma y, sigma z, sigma x equal to 0. So in general, when we replace x, y, z with dummy indices I and j, then we can write it as 2 delta ij I. I is the identity matrix and delta ij is the Kronecker delta. So delta ij will be equal to 1 if I is equal to j. It means that if sigma x anti-commutes with sigma x, then result will be 2 I. I is the identity matrix. So if I is not equal to j, which means that we are dealing with two different Pauli matrices like sigma x, sigma y, or sigma y, sigma z, then delta ij will be 0. So the product will be 0. So anti-commutation relations are important for spin-half systems. For example, fermionic spin systems, and commutation relations are important for bosonic spin systems. So this is the basic difference between commutation and anti-commutations of Pauli matrices. I hope so you find this video useful. I will be back with new video. Enough for today. Allah Hafiz.